I want to remind you that linear maps or linear transformations to start with are just functions, right? They're functions between two vector spaces that satisfy some additional properties. As functions, we can do what we usually do with functions, or one of the things we do with functions, which is operations on functions. We know how to add functions. We know how to multiply a function by a scalar. We know how to multiply functions. Okay, so we may ask what do these notions give for linear maps, and we'll see that up to terminology there's a similarity, although things are not precisely the same. So here's our first definition. So definition, let T from V1 to V2 and S from V1 to V2 be two linear maps, and let, I called it alpha, be a scalar in the field F. Everything has to be defined over the same scalar field F. So we define T plus S just like we do for functions. So what does it mean to define a new linear map? We have to say what it does to little v in V1. Okay? So what does it do? The very most expected thing, it's just T of V plus S of V. So that's how we add linear maps. And if we want to ask what is alpha t, again, a linear map, what does it do to a vector v? It just takes alpha times T of V. Okay, so that's the definition of these two new linear maps. Okay, so the first thing one has to show, as functions, we know it's just the same definition for functions, but is it true that T plus S is still a linear map? T was a linear map, it satisfied some properties. S is a linear map, it satisfies some properties. Is the sum a linear map? Does it satisfy that T plus S of V plus U is the same as T of V plus U plus S of V plus U? And those are very simple things to verify, and please do it on your own. So verify that T plus S and alpha T are linear. Okay, let's do an example. So I want to give you two maps. Both maps are going to be maps from R2 to R2. So I'm going to tell you what T does to a vector of the form AB and what S does to a vector of the form AB. So T of AB is going to be defined by multiplying by a matrix. We already know that this is a linear map, and we had a long discussion that any linear map has a matrix representation. Okay, so this is what T does to AB in R2, and S of AB is going to be defined as 0, 3, 1, negative 1 times AB. Okay, so we know that these are well-defined linear maps from R2 to R2. Do you agree? Okay, so let's see what T plus S is. So T plus S is going to be a linear map on the same domain space with the same range space. Let's see what it does to a vector AB in R2. So what does it do? By definition, it does T of AB plus S of AB. Right? That's how we defined the addition. Okay? So what is T of AB? I'm just writing what T of AB is and what S of AB is. So T of AB is 1, 2, 0, negative 1 times AB, plus S of AB is 0, 3, 1, negative 1 times AB. Right? That's precisely what these maps T and S do. Now, by rules of matrix multiplication, I know we have distributivity. So if I have a matrix times a matrix plus a matrix times the same matrix, this is the same as the sum of the matrices times AB. So this is the same as 1, 2, 0, negative 1 plus 0, 3, 1, negative 1, the sum of the matrices times this matrix. This is distributivity of matrix multiplication with respect to matrix addition. Do you agree? Okay. So what I get is I just add the matrices, right? So the addition is what? 1, 5, 1, negative 2 times AB. Okay. And note that en route, I didn't have to actually calculate this in terms of AB, to actually find what the image is, what the image looks like as a vector in R2. Okay, that wasn't necessary. Okay, so at least in this example, and that's going to be a theorem a bit later on, but at least in this example, adding the linear maps corresponds, okay, works well, agrees with adding the matrices that represent them. Okay? But this is in the case where the maps are indeed represented by matrices. Okay? So we know that's a general case. We know we can always do that. And we can state this as a general theorem that will follow a bit later. Okay? So matrix addition corresponds to map addition, to linear transformation addition. Okay, good? Okay, so, and you can verify, by the way, that it will work the same for multiplying by a scalar. Okay, you can take a scalar 5 and calculate what is 5t, and then see that 5t corresponds to 5 times the matrix A that represents t. Okay, so there's a certain compatibility here. Now things get a bit more interesting when we want to define TS. Not T plus S, but rather TS, because there's a little twist. Okay, so what's the twist? Nothing too complicated. So the definition is as follows. So we're going to have a map T that goes from a space W to a space U, and then a map S that goes from V to W. Both of these are linear. Okay? And the picture you should have is the picture of so let me first write the definition and then write the picture. So TS, this is going to be a new linear map. What does it do to a vector V? By definition, it does T of S of V. So this is, in terms of functions, this is what we called composition of functions. Okay? So you first do S of V sends you into W, and then you do T to what you got. And that's well defined because T is defined on W and takes you to a vector in U. Okay? So this is called, you can call it composition of linear maps, okay? But the notation is the notation we usually use for products. Okay? We don't have this, in functions usually we put a empty circle here. Okay? And that's not the notation we use here. So this is slightly confusing. The notation for composition of linear maps is the notation we're used to seeing for multiplication. And you might ask, huh? Why would somebody do such a confusing thing? Okay, and there's a good reason for it, which we'll see in a minute in an example. But let me just emphasize here that this, the picture you should have in mind, and sometimes drawing these things helps. So we have V, a vector space, then we have the map S sending us into W, and then we have the map T sending us into U, right? And then we can compose, the composition goes directly from V to U, okay? And the composition is denoted, by the way, this is something else that is a bit confusing. The composition is TS, right? Because we first do S and then we do T. Okay? So this is something you should be already used to seeing with functions. That's how we compose functions. Okay? Good? Okay. So let me emphasize this. TS is the composition of T and S, although the notation is TS rather than T composed with S. Okay, so it's the notation we're used to seeing for functions. So why is that? And let's see an example. Or maybe before we see an example, let's prove that this is indeed linear. Okay, why is this a linear map? So let's start with that. So let's write it as a little claim, tiny theorem. TS is linear. Prove. So how do we usually prove something like this? We just follow the definition. There's not much we can do otherwise. So let's see, what do we need to show? We need to show two things. We need to calculate TS of a sum, U plus V, and we need to calculate TS of alpha V, right? And we need to show that here the alpha can be pulled out, and here that it equals T of the sum, T of S of the sum. Okay, so let's see what we get. Sorry, TS of one plus TS of the other. I'm confusing myself. Okay, so by definition, TS of something is T of S of the something. Do you agree? That's the definition of this product, which is actually composition. So since S is a linear map, we know we can write this as T of S of U plus S of V. Do you agree? Okay. Now, since T is a linear map, T of a sum is T of one plus T of the other. So this equals T of S of U plus T of S of V. Good. And now, by definition, T of S of U is nothing else but TS of U plus TS of V. So this proves linearity in terms of addition. Do you agree? Okay. What is TS of alpha V? Same thing. T of S of alpha V. Alpha can be pulled out of S. So this is T of alpha S of V. And then it's T of something, alpha can be pulled out because T is linear. So it's alpha of T of S of V. And again, by definition, this is alpha TS of V. Okay? Very, very simple. You could even say trivial, as long as you understand what you need to prove, what you need to show. Good? Okay. So we know that TS is linear. Let's do an example. Let's use exactly the same maps that we had in this example. So this is T, this is S. Now we want to see what is T times S. Okay? So I'm going to erase this.
When using your proof, we have to show first that T and S are linear, right?
No. The definition starts with the fact. You can only define it for maps that are linear. So in the definition we wrote T and S are linear, then we define the composition. Okay? You can't add, you can't expect to add a cat and a dog and then show that the product is linear. Okay? you're adding linear transformations, you can expect maybe the product or the sum or whatever to be linear. Okay. Okay. So what is TS of AB in this example again? Okay. So we know what it is because we know the definition. It's T of S of AB. It's composition, right? So what is T of S of AB? So I'm going to first replace S. S of AB is this. So it's T of 0, 3, 1, negative 1 times AB. Do you agree? And now I know what T of something is. It's this. So this is 1, 2, 0, negative 1 times whatever this is. 0, 3, 1, negative 1, AB. Do you agree? But now, these are all matrices now, right? And for matrices, just like before I knew the distributivity holds, I know here that associativity holds for matrix multiplication, right? So instead of multiplying this times this, I can multiply these first and then multiply by this. So this is the same as 1, 2, 0, negative 1 times 0, 3, 1, negative 1. Multiply these two first and then multiply by AB. Do you agree? And if you want to know what it is precisely, all you have to do is calculate the product of these two matrices. So it's 0 plus 2, 3 minus 2, 0 minus 1, and 0 plus 1. Is that correct? Yep, times AB. So what we just discovered is that the product of the linear maps, what is at least notation-wise looks like the product of linear maps, is compatible with the product of the matrices. And that's the reason for the notation. Okay? So the precise statement is composition of linear maps is compatible with matrix multiplication. Okay? So composition of linear maps is compatible with matrix multiplication. Multiplication. Good? And in a sense, okay, so one way to look at matrix multiplication, you may ask, why is matrix multiplication defined in this rather weird way? Okay, why is this the way we multiply matrices? Okay, so in fact, matrix multiplication, this statement is an if and only if statement, right? The word compatible says that this is compatible with this, but the other is compatible with the first one just as well, right? So matrix multiplication is compatible with composition of linear maps. Okay, and in a certain sense, that's why matrix multiplication is defined the way it is. Okay? And now you should not think of this notation as confusing any longer. Okay? It's confusing because what it really is the composition. But what it really does is the same as matrix multiplication. Okay? Good? Okay. So composition of linear maps is compatible with matrix multiplication. This is, of course, not a theorem, at least not the way we gave it here. It's just a conclusion from an example, but it is going to be a theorem, and we're going to prove it a bit later on. Okay? Okay. I want to show you one more example. In this situation, why the composition of the other way around is defined as well. right? Because this is a map from, both these maps are from the same V to the same V. They're both maps from R2 to R2. So you can either do first S and then to the result do T, that's what we did here, but just as well you can do first T and then to the result do S. That's just as well defined. Okay? So let's see what S times T is for this example. Let's write it here. So what is S times T of AB for that precise example? So by definition, it's S of T of AB, right? T of AB, so we can skip steps. We know what it is. We need to multiply the matrices in the other direction and then operate on AB. So let's write the matrices. The matrix for S was 0, 3, 1, negative 1. The matrix for T was 1, 2, 0, negative 1. And then that acts on AB, right? And the product of the matrices in this order, we would be surprised if it would be the same as the product in the reverse order, right? We know that matrix multiplication is not commutative, right? So what do we get? We get 0 plus 0. So we get a 0 here. 0 minus 3. 1 and 2 plus 1, 3. So that's the matrix representation of ST. Okay? And so this is the matrix for ST. The matrix for TS we saw on the previous board was 2, 1, negative 1, 1, and they're different. Okay? So in general, if TS is defined, there's no reason for ST to even be defined. Let's look at this board a minute, right? If saying that TS is defined means that the, means that the composition works in this direction, okay? The range of S is included in the domain of T. That's when we can define this. For it to be defined the other way, we need U and V to be the same, right? We need to be able to compose the other way around. And in general, that doesn't hold, right? That's a special phenomenon. But even when it does hold, even when both are defined, for example, when we're working with linear operators from a space to itself, they're usually not equal. Okay, so let's write that. In general, when TS is defined, ST may not be defined. Right? It's not necessarily defined. Okay? But even if it is, even if both are, usually ST is not the same as TS. Okay? And this usually is precisely the same statement as matrix multiplication is not commutative. Okay? Okay. I want to write down 2 more examples and from them move on to some more definitions. So do we want to erase this? Let's erase here. So here's a couple more examples. So let's look at M2 of R and take a map, we're going to call it S, that sends us to R4. And then take a map, which we're going to call T, that sends us to R3 of X. And the maps are going to be the following. What S does to a 2x2 matrix is send it to A plus B, 0, C plus D, 0. That's a vector in R4, right? And you can see that it's going to be a linear map because each entry here is a linear combination of the entries here. We already know that. Okay? And what T does, T of a general vector in R4, let's call it alpha, beta, gamma, delta, right? These are Greek A, B, C, D. What it does is send it to the polynomial beta plus delta x squared plus beta plus delta x cubed. Okay, and again, you can see that each of the coefficients here is a linear combination of these, therefore this is a linear map as well. Okay, and we can compose them, right? The domain of T is the range of S. We can compose them. So what is TS? TS is something that operates on M2R, so I have to see what it does to a matrix of the form A, B, C, D. And what does it do? It's T of S of the matrix. So it's T of A plus B, 0, C plus D, 0. Do you agree? And T of this thing is the polynomial, right, that takes beta. What is beta? 0. What is delta? 0. So what's this polynomial going to be? 0. This is going to be the 0 polynomial. Okay? So when we take this linear map, which is obviously not the 0 map, and we take this linear map, which is obviously not the 0 map, the composition is the 0 map. Okay? And that shouldn't be too weird, because we know that we can multiply matrices that are not 0 and get the 0 matrix. Right? There are what we call 0 divisors in matrices. Okay? So that's one. So let's write that. TS is the 0 map. What we defined as the 0 map in terms of linear transformations. It sends everything in every 2 by 2 matrix. It sends to the 0 polynomial. Okay? By the way, what is ST in this case?
It's not defined.
It's not defined. It doesn't make sense at all. Right? ST would be take a vector here, send it to a polynomial, then do S to it. But S doesn't have a clue what to do with polynomials. S operates on 2 by 2 matrices. Okay, so let's maybe write that. Note that ST is not defined in this case. Okay, let's write another example, yet one more example. Each of these examples demonstrates some phenomenon that you can encounter. That's why I'm writing several examples. So here's another example. Let's take the map going from R3 to R3. And this is going to be the map S. And then there's going to be a map T that again sends us to R3. And how does it work? So I have to tell you what S does to a vector x, y, z. Right? And what it does is it sends it to x, y, 0. Do you remember what we called this map? A projection. Remember, this is a projection. It takes a point in 3-dimensional space and projects it onto the xy plane. Okay? Doesn't care what its z-coordinate was. Every point above the point xy is going to be sent to xy, 0. Okay, so this is a projection, and then T again operates on guys like this, so T takes an x, y, z in general, and sends it to minus x, y, z. What did we call a map like this? A mirror is slang. What did we call it more formally? A reflection. Okay, so T reflects with respect to the yz plane. Okay? Okay. So what does TS do? TS, what does TS do? So TS of XYZ, TS of XYZ is T of S of XYZ, right? S of xyz is xy0, right? And then t of that, so it's t of xy0, and what is t of that? Minus xy0. Do you agree? Okay, so let's write that this is a projection, and this is a reflection. Okay, so in this case, the composition is defined in this order. By the way, what is ST in this case? What is ST of xyz? It's S of t of xyz. So it's S of minus xy0, sorry, minus xyz, right? We first reflect and then we project. What do we get? The same thing. So in this example, both maps are defined, both are operators, so it makes sense that they're defined, and in fact they're equal, right? So in this example, ST and TS coincide. Good? Okay. So here's another definition. Here's another definition. So we know what it means to compose linear maps. We know what it means to add them and multiply one by a scalar. Division is probably not going to make sense, right? Just like we don't have division of matrices, right? It's probably not going to make sense. But what could make sense is at least division in some sense, which is the inverse, right? So this is the following definition. So let T from V to V, now it's an operator, it goes from the space to itself, be linear, one-to-one, and onto. Okay, a linear map that's one-to-one and onto. As a function, what do we know? If a function is one-to-one and onto, it has an inverse. So as a function, T has an inverse. Right? And we're going to denote the inverse just like we do for functions. Denoted t to the minus 1. That's how we denote the inverse function, f to the minus 1. And t to the minus 1 goes from v to v, goes backwards, but they're the same space, so t inverse is still a linear operator, right? And what does the inverse satisfy? The property of being an inverse, satisfying that if you take t and then do t inverse, or if you take t inverse, so this is first doing t inverse and then doing t, but you could also do t inverse on top of t, first do t and then do t inverse, and both are going back and forth and will get you where you started. That's the property of being one-to-one and onto, right? That's the invertibility. So both of these are equal, and they're both equal the identity map, I. Remember I? I is the map that sends every little v to itself. Okay? So what's missing from this? Something is missing here. Everything here holds because these are functions. What's missing is, why is T inverse a linear map? That's not in the definition. That again requires proof. Okay? So again, a claim, proposition, T inverse, which is the inverse function of T as a function, is not just an inverse function, it's a linear map. We need to prove that. Okay. So again, how do we prove this? Maybe let's take a new board. How do we prove? I'm going to regret erasing stuff, but I don't have much of a choice. So how do we prove this? We have to show that if we take v plus u and do t inverse to it, we get t inverse of v plus t inverse of u, right? That's, and likewise for a scalar product. Okay, so let's do it. So proof, we want to take t inverse of a sum, v1 plus v2, and show that this equals to t inverse of v1 plus t inverse of v2. That's what we need to show. So let's denote remember that t inverse is the inverse of t. That's how it's defined. So v1 is t of something, right? Every vector is t of something because the map is onto. So I'm going to denote v1 is going to be t of w1, and v2 is going to be t of some w2, and not just some, a unique element. Okay, it's one-to-one and onto. So let's so w1 and w2 exist and are unique because the map is invertible, because it's a one-to-one and onto map. Okay, so t inverse of v1 plus v2 equals t inverse of t of w1 plus t of w2. Right? And, okay, can I write that this equals t inverse of t of w1 plus t inverse of t of w2? No. That's what I'm trying to prove. I'm trying to prove that t inverse is linear. Right? Taking the next step to be t inverse of this plus t inverse of this is using the fact that it's linear, but I don't know that. That's what I'm trying to prove. Okay? What I know is linear is t. That I do know. So I can go the other way and say this equals t inverse of t of w1 plus w2. That's because t is linear. Good? Okay, and now t inverse of t of something is the identity, is w1 plus w2, right? That's the property of being an inverse map. If you do t and then do t inverse to what you got, you get to where you started. And what was w1 plus w2? w1 plus w2, well, t of w1 is v1, so w1 is t inverse of v1. And w2 is t inverse of v2. Good? Clear? And that's what we wanted to prove. Okay, so this proves that t inverse respects addition, and then you need to prove the same thing for, so I'll leave that as an exercise. Use rather similar arguments to show that t inverse of alpha v equals alpha t inverse of v. Don't be tempted to use this fact in showing it, right? You can only use the linearity of t along the way, and the fact that every vector is t of something, okay? Because it's a invertible map, okay? Okay, let's look at some examples. Let's start with looking at this example here. Okay, so is the map T here invertible? Does it have an inverse? T sends xyz to minus xyz. Can I go back? The answer is yes. And what's the inverse map of T? It's T itself. T and T inverse are the same map. You take 1, 2, 3, you send it to negative 1, 2, 3. Right? So all you do is add a minus sign to the first coordinate, and that's precisely what you do if you want to go the other way. Right? So in this example, t and t inverse both exist and they're the same. Do you agree? Do you see that? Okay. What about S? S doesn't have an inverse, right? What S does, S projects, it kills the z coordinate, makes it 0, there's no way to go back, right? So what's hidden here, the reason you can't go back, is that S is not onto, right? And not one-to-one, right? It sends everybody, doesn't matter what Z they have, to 0, right? Another way of saying it is that S has a kernel, right? Okay, so S is not invertible. So T equals T inverse, whereas S inverse does not exist. That's in this example. Do you agree? Okay, so note that we're saying it in various ways. Just as a function, this function is not one-to-one and onto, right? But in terms of being a linear map, another way of saying the same thing is that S has a kernel, a non-trivial kernel. Okay, and we know that having a kernel is the same as not being one-to-one. Okay, so everything with x and y being 0, you can put whatever z you want, and it's going to send you to the 0 vector. It's going to project you onto the origin. Okay, so it has a non-trivial, a one-dimensional kernel, therefore it's not one-to-one, therefore it's not going to be invertible. Good? Okay, what about, for example, the first example that we had, the one with the matrices, So let's, it's no longer on the board. Let's recall what it was quickly. So the first example that we had 3 examples so far. And the first one, at least T of V was a V, where A was the matrix 1, 2, 0, -1, right? So T of V was T of AB was 1, 2, 0, -1 times AB. That was T of the first example. There was also an S, but let's look at T first. Okay, so the claim is that T is invertible. Okay, and can you guess what the inverse is going to be?
The inverse matrix.
Right. T inverse is going to be represented by the matrix A inverse. Okay, and again, that's going to be a general theorem which requires proof. Okay, so let's see that T inverse is represented by A inverse. So first we need to find A inverse. How do we find an inverse matrix? We have various ways of doing it. Right, we put the matrix A, 1, 2, 0, -1. Then we put I here. And then we do row operations until we reach the canonical form here.
I form. We need to go to I.
I, right, but if it's invertible, the canonical form is going to be I, right? And here we're going to find A inverse. That was a theorem, okay? So what are we going to do? The first thing is I want to make this a 1. So I'm going to multiply R2 is going to become negative R2. So I get 1, 2, 1, 0, and then 0, 1, 0, -1, right? And then I want to make this 2 a 0, so I'm going to subtract from R1. R1 is going to become R1 minus 2R2. And what I get is 1, 0, 1 minus 2, right? Plus 2, minus 2R2. And then here I'm going to get 0, 1, well, this I'm not touching, in fact. Do you agree? And that's it. A just became I, so I just became A inverse. Okay? So this is A inverse. So A inverse, in this case, is the matrix 1, 2, 0, -1. And just a coincidence, but note that in this case, just like in the previous example, A inverse equals to A in this case. So, which happens to be A. Okay, that's not usually going to be the case. It just happened in this example. Okay, so this is A inverse. What we want to see is that A inverse is exactly the matrix representation of T inverse. Okay, so what do we need to show? What do we need to show? We want to see, is it true? Is it true? So let's recall what T does. T of AB is A times AB. So it's 1, 2, 0, negative 1 times AB. Right? And what that is A plus 2B. That's the first entry. And then 0 minus B. That's what T does to AB. Right? So if T inverse is really represented by A inverse, if I multiply this matrix by this, I should get back to AB. That's what it means to be the inverse map that sends this back to AB. Right? So let's see that. T inverse of A plus 2B minus B. The claim is that this is precisely A inverse, which happens to be the same as A, times the vector A plus 2B minus B. And if we're right, this is going to be precisely AB, and it is, right? It's A plus 2B minus 2B, which is A, and then it's 0 times this, and therefore it's B. Okay? So in this example, T inverse, we just said that. T inverse is represented by A inverse. Okay, good. So again, that's going to be a general theorem, and I'm going to leave it for you for practice. Find S inverse. There was an S in this example too. It was given by a different matrix. Find the inverse map of that. It's a linear operator, and it is invertible. Okay? We have tons of ways of deciding whether a matrix is invertible or not. Remember, that was a theorem with many, many parts. You can check the determinant is 0 or not. You can check that when you do row operations, you get to I. You can check that for any B, AX equals B has a solution. Remember, we had a lot of characterizations for being invertible. So S is invertible as well. Find S inverse and show that it's given by the inverse matrix of the matrix that gives S. Okay? Okay. So I want to write a couple more facts. So first of all, here's a theorem. Well, both of these facts are going to be theorems. So if T from V to V is a linear operator, remember that an operator is just a map from a space to itself, then T is invertible if and only if, as a function. When can you say that a function is invertible? If and only if it's 1 to 1 and onto, right? But as a linear map, there's a stronger statement. It's invertible if and only if T is onto, and if and only if T is 1 to 1. You only need to check one of them. And why is that true? Because of a theorem that we had previously. Okay, so let's write the proof. The proof is going to be a one-liner. The proof is going to stem from the fact that for a linear map, these two facts are if and only if. A map is onto if and only if it's 1 to 1, providing one thing, that the dimensions of the range and the domain are the same. That was the theorem that we had. And if it's a linear operator, they're of course the same because they're the same space. Okay? So the proof is we had a theorem previously that if the dimension of V1 equals the dimension of V2, and that theorem followed again with one line from the rank nullity theorem. Okay, you can look back and see how we proved it, that if this holds, then T is 1 to 1 if and only if T is onto. And that completes the proof. If it's one, it's the other, and then it's both if and only if it's invertible. That's a general fact about functions. I'm not going to prove it here. Okay? A general fact about functions. A function is invertible if and only if it's 1 to 1. Okay? Functions between sets, not linear functions. Okay? Good? Okay. And one last theorem for this clip, for this lesson. So if T and S are invertible, then TS is invertible. Remember that being invertible is defined for linear operators. Okay, so both of them go from V to V, therefore the composition makes sense. Okay, we can compose them, but the composition is going to be invertible as well. Just by writing this, it should make complete sense that it's true. If you do T and then do S, and you can go back on both because both are invertible, then you can go back on the composition, right? And what's going back going to be? And you tell me, what is TS inverse going to be? You can even say precisely what this is going to be.
S inverse.
Right. It's going to be S inverse T inverse in the other direction. And the reason is, so we'll prove it formally in a minute, but the reason is the following picture. So intuition. We have V. We have, so we did TS. So S goes from V to V. And then T goes on back to V. These are both operators. So TS is this map, right? So what's the map going backwards going to be? So here there's a map going backwards, T inverse. Here there's a map going backwards, S inverse. That's because both are invertible. And this map going backwards, on the one hand, it's going to be TS inverse, right? It goes backwards. But on the other hand, it's the composition of these two backward arrows. And the way we write the multiplication is we first do T inverse to V, and to that we do S inverse. So just like we write composition, right? We first do T inverse and then S inverse, and we write it like this. Do you agree? Okay, so that's the intuition, and this intuition is in fact the proof. Okay, the line between being intuition and being proof is very, very blurry here. So the formal proof would just be to write it a bit, really a bit more formally. So what do we need to show? We need to show, what does it mean to be the inverse? What it means to be the inverse is that if we take TS and multiply it by TS inverse, we should get the identity. That's how we defined the inverse map, right? So that's what we need to show. We need to show that if we take TS and multiply it by the inverse, we get the identity, right? So if we're claiming that this is the inverse, tell me if you're following the logic. Whatever TS inverse is, when I put it here, I should get the identity. That's the definition of being an inverse. My claim is that this is it. This is the inverse. So in order to prove it, I should put this here, multiply, and see that I get the identity. Do you agree? That's what it means for this to be, in fact, the inverse. Good? Is the logic clear? So how do I show that this product is the identity? I have to take a little v, do this to it, and see that I get v. That's what it means to be the identity. Okay? Is everybody following the logic? I didn't write anything. I didn't write a single equal sign yet. I'm just understanding what it is that I need to show. And then showing it will end here, right? It's going to be very easy, but you have to first understand what you need to show. Good? Everybody with me? Okay. So what is this? This is, by definition, the way we do a product of maps is do this, and to that do this. So this is TS of S inverse T inverse of V. Right? That's the definition of composition. Right? And what is TS of something? So this equals T of S of, that's what TS is, of S inverse of T inverse of V. How many do I have to close? 4. Right? And S of S inverse of whatever is like doing nothing. So this equals T of T inverse of V. Because whatever T inverse of V was, I did S inverse to it, and then I did S to it. I got back to where I started. And likewise here, this equals
V.
I of V, which is just V. Okay, so we proved that indeed, if we take this map and compose it with this, we get the identity map, and therefore this is the inverse. Okay? And I recommend, so this is abstract, I recommend for practice, take example 1, for example, the one with the matrix, what was it? 1, 2, 0, negative 1, and then there was a matrix for S, and show it. Find TS, I think we already did that, multiply them in the other direction, and show that you indeed get the inverse map, that it does the inverse operation. Whatever TS does, S inverse T inverse sends you back. Okay? So practice it on an example just to get the feeling that it's the right thing. Okay? Okay, so this completes this discussion of operations on linear maps. Okay? What I want to do in the next lesson is to argue formally, to write it as theorems, that indeed there's a compatibility between the operations on the linear maps and the corresponding operations on the matrices that represent them. Okay, so that's what we're going to prove next.